Okay, dear students, in the second class of the course called Open Channel Hydraulic Engineering for Civil Engineering, so this starts today from uniform flow, gradually varied flow, and water slope profiles and water surface profile. Now, in the last class we have taught that how the fluid dynamics approach we can put into our knowledge in the open channel hydraulics by quantity equation, energy equation, and the momentum equation based on the application of the hydraulic jump. And we studied hydraulic jump, different sequential depth for particular specific energy with round number. Now in today's class we will cover the section of uniform flow and gradually varied flow. Now in order to understand the uniform flow, now we already know that the discharge, when the discharge is unchanged in respect of time, we call it as a steady flow, right? This is a steady flow. Well, when the flow depth doesn't vary with respect to space or distance, here it is x, then we can classify the flow as uniform flow. If the flow property contains two types of things, then we call it steady uniform flow. Okay? Now assume a channel, assume there is a water profile. Now with a particular height y, this is our bed and this is our datum level with a particular angle z, or you can see in the last class we learned that this section is the kinetic energy or velocity head, this section is the pressure head, this section is the potential head. In that case, when now first of all we need to understand that the hydraulic gradient line or the energy gradient line, this is called EGL. As we have learned before, this is called EGL, means energy grade line, and this is called HGL. Now, when this slope to that tangent, this slope, this is equal to SF, called friction slope. This thing for the slope we are getting due to the hydraulic grade line is called SW, or water surface slope, and then this the slope we get due to the bed is called the S0, which is the bed slope. Now for a perfectly ideal rectangular flow, uniform flow, these three values will be always the same. Now if you analyze this thing to have some mathematical equation, we can see that what you can see that when now the water is flowing to that direction with a particular velocity, say v, or say Vm, which is the mean velocity of water. Now, the weight of the water that actually walks in a direction something like this, where it is considering an angle of theta, which is actually the same of the bed slope, then these things becomes W cos theta, and this force driving the water to flow to that direction, it becomes W sin theta. Now, what is the physical significance of uniform flow? The physical significance of the uniform flow will occur at a certain time where the resistance force due to the surface area of bed and side. Now, try to understand a simple thing, which is, imagine this is the cross section of the flow or the river or the channel. Now, this is the cross sectional area and it has a certain length, channel length, and this we can think of the weighted perimeter. Now, when the area or the surface area which is giving the restriction or the resistance to the mean flow, what area is that? Which area is that? It will be the area of bed area by the side wall area, isn't it? The total surface area of the bed and slope will give the resistance force for the water, so it can have the energy to not to flow against the W sin theta force. Now, in case of uniform flow, what will happen? The W sin theta, the driving force, will exactly be equal to the resistance force, or say R. That is one of our condition to meet when we want uniform flow in a certain channel. Now, when the resistance force is increasing, if the resistance flow is increasing, then what happens? The velocity, the rate of velocity, the rate of change of velocity, acceleration will decrease. And if the W sin theta, the component of the weight in the direction of velocity will increase, then automatically the acceleration will increase. Now, and what will happen except this acceleration will increase, the velocity is also increasing. Now, for a constant discharge, if we provide a constant discharge, constant Q, then what happens? If at a particular constant discharge the velocity is increasing, the flow depth will automatically decreasing. And if the velocity acceleration is decreasing, velocity will decrease and the flow depth will increase. That's what happens in a ideal uniform flow. Now, when the flow depth is increasing with respect to the space or distance, then we can't just call it a uniform flow. Okay. Then when the flow is get settled and the change of these things, these two terms get balanced in an equilibrium state, then we get a depth of y is equal to yn, which is called the normal depth of the flow. What called normal depth. to another chart. Now just draw that thing here also. Now this is the cross section of the channel. This is the sectional view, as you can see. Now if we want to have the velocity from this thing, what we need to do? Tell me. Oh, and one another example. If there is a particular soil type or slope, something like this. Imagine this, then it will decrease further, then it will increase a little bit. If this kind of slope exists, then what we will do? Now for this part we can have a different theta 1 or S1. For this part we can have a different theta 2 or S2. For this part we can have a different theta 3 or S3. Now when this thing happens, then due to the decrease of the slope, the water surface profile will decrease a little bit, isn't it? Then here it is uniform. Now here what happens? It will have a lower depth. Now after certain time it will gradually increase like this. Then we can have another what? Normal depth, yn1, yn2 we can write. And for this channel, the flow will now this. It automatically the depth will vary with slope in uniform flow, and the uniformity of the flow is remain throughout a single section of slope. And then we can write this yn3. Now the few scientists or researchers have discovered the velocity value of the uniform flow. The first one is Chezy and the second one is Manning. These are two very important formula even in industrial application. Now what he did, so now Chezy's first formation of the formula was something like this, where he parameterized the mean velocity with the hydraulic radius A by P, as you know, I have taught in the last class, and the S is the bed slope. Now what they did, they put some exponential of x and y with R and S to have this thing parameterized or validated. Now as you can see, the resistance, now in the side wall it will give a resistance which is called resistance force by area. What is saying, resistance force by area will proportional to the square of the mean velocity. For Chezy says, I repeat again, the total resistance force generated by the bed surface area and the side surface area of the channel per unit area, the value is proportional to the value of mean velocity whole square. Now as you can write, dF by dA equal to kVm square. Now this thing happened for a what? For unit area. Now if you further derive it, as you can see, write dF equal to dA kVm square. Now integrate that thing from 0 to F, 0 to A. Write it FF because it is based on the. Now the one thing now the side wall or the bed, it has a particular roughness coefficient or friction coefficient. Now due to the roughness, now more the roughness I am having from the side wall or the bed, the more resistance force I will get from this surface area. Then a roughness coefficient is used, so we can derive the total frictional force given by that particular surface area. Now there is dF. Now we can have this. Now that will be equal to A. Now what is the actual A here? This is not the cross sectional area. This is the total area of the bed and the side wall. Now if this is the cross section, the total side or bed area is dependent by its parameter and its length. Then it will be AS equal to PL. Write it here. PL K V N square. This is our resistance